In this series of videos, we're going to be exploring the first major application of the principles of dynamic equilibrium, studying solubility and solution chemistry in general. Solubility as a measurement simply measures the maximum amount of solute, the chemical that is dissolved, that can be dissolved within a specific volume of solvent, that being the chemical that does the dissolving. So in this case, if we look at the dissolving process of calcium carbonate and the reverse process of dissolving, we can see that we're mixing two solutions here. Now the background for this is one of our solutions contains the cation Ca2+, and the other solution contains the anion CO3 2-, and eventually these two ions will reach a certain point where they exist in a concentration that is too high so that they eventually join together and form this white cloudy solid within the solution, which is what we call a precipitate. Now, if we see a precipitate forming, we have just discovered that the solution in question is what we call saturated. Remember that this word from organic chemistry, used in the case of saturated hydrocarbons, is simply a fancy word that means full of, meaning that if we say this solution is saturated, that means that it is full of dissolved ions, so that these ions cannot stay dissolved, and instead they come back together and form the precipitate because the solution is already full of enough ions. Now we can represent saturated solutions in two chemical reactions that are actually the reverse of each other. So if we consider the dissolving reaction of calcium carbonate, we know that water will pull the two ions apart in order to form Ca2+ and CO3 2-. This is our dissociation reaction. The type of reaction where we put an ionic solid into water, and water uses its polarity to attract and pull these two ions apart from each other. However, this reaction is not the reaction that we're seeing here where the precipitate forms. We're actually seeing what we call the precipitation reaction, the formation of a precipitate, which is actually the opposite of a dissociation reaction, where our solution contains too many of each of the ions that make up the solute, so those ions use their charges in order to attract to each other and come back together and form the solid form of the solute once again. Now let's talk about the relationship between these two in the process of making a saturated solution. So in this solution here, we do not see a precipitate being formed, meaning that if we have a specific amount of calcium and carbonate ions, we have not reached the saturation point because there is no precipitation reaction that is happening. If this is the case, we are dealing with what we call an unsaturated solution, meaning that we can dissolve more of each of these ions into the solution. What this means, because we have no precipitate here, that our precipitate or precipitation reaction is not happening, meaning that the rate of dissociation must be happening faster than it. However, when we get to the point where the rate of dissociation begins to equal the rate of precipitation, this is where we start seeing our precipitate forming. This is what we call the saturation point. And the farther we exceed the saturation point, or further rather, the more noticeable or the more obvious our precipitate becomes, and the greater percentage of the solution it begins to take up. Now, when we get to this point, does this mean that the dissociation reaction is no longer happening? Well, no, that doesn't make any sense, because water will always be attracting to the charges of each of the ions in the solution, and therefore pulling apart the solute. So in this case, we can't say that only one of these reactions is happening. We have to say that both of them are happening. And if the rate of dissociation and rate of precipitation are equal, we can write an equilibrium expression where we have our solute on one side, solid calcium carbonate, and our dissolved ions, Ca2 plus and CO3 2 minus, on the other side, like so. Now, because saturated solutions are at equilibrium by definition, because the rate of dissociation is equal to the rate of precipitation, that means that we can write a KEQ expression for them like this. Now, KEQ expressions of dissolving reactions are very easy to write because the solute in the reactants exists in its solid form, which means that its concentration is constant, as we discussed in the previous unit. Therefore, its concentration being constant does not appear in the overall expression, because we would simply incorporate that concentration into the actual equilibrium constant itself, and all that we would end up with is the product of the concentration of each of our two ions. And in fact, that gives us a hint as to why the new version of KEQ is written the way that it is. So if KEQ is written for solubility reactions the way that it is, that means that it is only measuring the product, because again, there is no denominator other than 1 in this case, because the concentration of our solid solute is constant, so we only have the product of each of the different ions, and because each of these ions measures the concentration of the ions that is dissolved within the solution, we say that these are the product of the solubilities of each ion. And for that reason, we don't refer to our equilibrium constant as KEQ, we give it the name KSP. In other words, the solubility product KEQ constant. In the next video, we'll look at how to use this in calculations, but for now, remember we're looking at how this is an application of equilibrium, and that means that we can look at the requirements for forming a saturated solution. So in addition to the same requirements as dynamic equilibrium, that being concentration of products and reactants are both constant, no macroscopic changes, etc., we can list off these definitions as an expansion to that. So in a dynamic solution equilibrium, we know that our rate forward must be equal to our rate reverse, which means the rate of dissociation and rate of precipitation must be equal. And in order to have the rate of precipitation at all, that must mean that we must have a visible precipitate within solution, because if we don't, that means that there is no precipitation.